Hello students, welcome back to your physics class, and today we will be continuing our discussion on simple harmonic oscillations. So if you remember, in your last class I have put forward a definition of simple harmonic oscillations for you. So the definition is a very physics based definition. It says that the restoring force acting on the oscillatory particle at every position of its path is directed towards the equilibrium position, or the force tries to restore the position of the oscillatory particle to its equilibrium position if the oscillatory particle is undergoing this special kind of motion known as simple harmonic motion. And I also told you that this restoring force is always directly proportionate to the displacement of the particle at every position of its path. But today I am going to put forward an alternative definition for simple harmonic motion, and this definition may sound a little bit more mathematical to you. The definition that I am going to put forward is the displacement of a simple harmonic oscillatory particle varies as a sinusoidal or cosinusoidal function of time. So what I'm saying is, if a particle is undergoing simple harmonic motion, then its displacement is a sine or a cos function of time. Now, how do I get this alternative definition? Eventually, in later classes, I will actually write down the equation of motion of a simple harmonic oscillatory particle for you. I will solve the differential equation in details and show you that indeed the displacement is a sine or cos function. But today, I try to give a physics-based justification of this alternative definition. So I'll give you a pictorial demonstration which will depict why we can express simple harmonic motion as a sine or cos function. So let's begin. So what I do in this pictorial depiction for you is, I represent the position of the particle undergoing simple harmonic motion, its position as it carries out its motion, its position at different instants of time as it carries out its simple harmonic motion, as points along the circumference of a circle. So these positions I represent by points along the circumference of this special circle. Why is this circle special? Because its radius, the radius of the circle, as you see, is a, that is, it is equal to the amplitude of simple harmonic oscillation. So the radius of this circle is equal to a, the amplitude of simple harmonic oscillation. And suppose at instant of time t, the position of the oscillating particle is p. Okay. So as you see that I have a two-dimensional picture. The circle is in two dimensions. These are the x and y coordinates respectively. But as we know, simple harmonic motion is a linear motion. Simple harmonic motion is a linear motion. Why is the motion linear, I say? Because as we have said, the force the restoring force acting on the particle undergoing simple harmonic motion, that is directly proportional to its displacement. So if its displacement be x, force is directly proportionate to x. Of course, the direction is such that the direction is opposite to the direction of displacement, because the force is trying to reduce the displacement to zero, because it is trying to bring back the particle to equilibrium position. But the force is directly proportional to displacement. So it's directly proportional to x if x is the displacement. So it is not proportional to x square, x cube, or x to the power half. It is proportional to linear power of x to the power 1. So the motion is linear. And as the motion is linear, that's why in order to depict the displacement, I would be taking the projection of the position P of the particle either along the horizontal axis or x-axis, or along the vertical axis y-axis. So in this case, I choose to depict the displacement as its projection along the horizontal axis or x-axis. So when the particle is at position P, its displacement is along x, the projection A cos omega t, where omega t is the angular displacement, omega being the angular velocity and t the time taken to reach position P. So omega t is the corresponding angular displacement. So as we see here, we have written the displacement to be of this form. Okay. Now let's say the particle is at position Q at time t0, which we choose to be the initial time or the zero of time. So t0 is chosen to be the zero of time or the initial time. So the particle is at position Q at initial time. Okay. So if t is 0, what is OA equal to? If t is 0 at Q, t is 0, so OA is equal to A, correct? And of course t is 0. So we would represent the time evolution of displacement of the particle by a simple curve like this. So along this curve, along the x-axis, we have time, and along y-axis, we have displacement. So displacement as a function of time, we are going to represent by this curve. And as we see in this curve, at t is equal to 0, the particle is at position Q at t0, and its displacement is A, the maximum displacement at extreme position. Okay. Then the particle moves from position Q to position R, and when it moves from position Q to position R, omega t, the angular displacement, increases to pi by 2, as we see. So omega t is increasing to pi by 2, and so at position R, omega t is equal to pi by 2, and we know the corresponding displacement OA when we fit in omega t to be pi by 2 is 0. So the displacement reduces to 0. And we can also see that when omega t is equal to pi by 2, then what is omega equal to? Omega is equal to pi by 2t. And when we fit this into the relation that t is equal to 2 pi by omega, we know that this is the relation between time period and angular frequency. Because what is the relation between time period and linear frequency? Time period is equal to 1 by linear frequency. And when we put in the relation between linear frequency and angular frequency to be omega is equal to 2 pi into f, then we get that T is equal to 2 pi by omega. Okay. So this is the relation between time period and angular frequency. And using this in this relation, when we fit in omega is equal to pi by 2t, then we get the relation that using this t is equal to capital T by 4. So when the particle is at position R, then the corresponding displacement OA is 0 and the corresponding time T is 1/4 the time period of motion. So in this curve, from position Q, the particle moves to position R, where the time required is 1/4 the time period, and the displacement of the particle at position R is 0. So the particle moves here, this way. So what is happening is our particle is beginning its journey from one of the extreme positions. Okay, and from one of the extreme position, it is moving to the equilibrium position when it is moving to position R, and the time required to move from extreme position to equilibrium position is 1/4 the time period. Okay. Then the particle moves from position R to position S. And when the particle moves to position S, omega t increases to pi. So when it moves to position S, omega t is equal to pi. And when omega at S, omega t is equal to pi, and so OA, the displacement, when we fit in omega t to be pi, we get from this relation that OA is equal to minus A. So the displacement is minus A. And what is the corresponding time? Again, we have when omega t is equal to pi, omega is equal to pi by t. And when we fit this into this relation for time period, we would see that when this happens, then time is equal to half the time period. Small t is equal to capital T by 2. So time is equal to half the time period. So in this curve, we have at position S, the displacement is minus A. So this is minus A, and the time required is half the time period to come down to this point. So from extreme position, the particle moves into equilibrium position in 1/4 the time period. Then at 1/4 more time period, it reaches the other amplitude position, minus A. So total half the time period is covered in moving from one extreme position to another, in moving from plus A to minus A. Then the particle moves from position S to position L. And again, we can see that when particle moves to position L, then the corresponding time is, or omega t is 3 pi by 2. And so at L, we have omega t is equal to 3 pi by 2, and if we fit that in, we will into the relation for OA, we will see that OA is equal to 0 for at L. For omega t is equal to 3 pi by 2, and if we write omega as 3 pi by 2t and fit this into this relation for time period, we will see t will be 3/4 the time period. Okay, so O at L, the displacement is 0 and the time required to reach L from Q is 3/4 the time period. So again, over here at position L, the displacement is 0, and the time required to reach here is 3/4 the time period. Okay, and so the particle comes from one amplitude plus a equilibrium displacement 0 to displacement minus a in half the time period, and in 3/4 the time period it again comes back to the equilibrium position. And from the equilibrium position, coming back to equilibrium position at position L, it then again moves to position Q. So it again reaches the other amplitude, and it completes one complete motion, one complete oscillatory path. And the time required to come back to Q over here, the time required is equal to T is equal to capital T. When it comes back to Q, it's amplitude plus A. And if you look at this function, at this curve, you can easily see that the displacement, if we write the displacement as x, x is equal to A cos omega t. So it is represented by a cos function, or we can write it as a sine function, A sine omega t plus pi by 2 x. Okay, x is equal to A sine omega t plus pi by 2. Okay, so here A is the amplitude of motion. The motion is a sinusoidal function of time, as we see, and the initial phase or epoch here is pi by 2. The initial phase or epoch is pi by 2. So if we represent the motion as x is equal to A sine omega t plus delta, the phase factor delta is known as the initial phase or epoch. Okay, and it's this initial phase or epoch that decides from which position the motion of the particle begins. Here, since the initial phase was pi by 2 in our consideration, the motion began from the extreme position or amplitude position. We can easily see that if delta is equal to 0, if the initial phase delta happens to be 0, then x is equal to 0 at t is equal to 0. If delta is equal to 0, then x is equal to 0 at t is equal to 0. So if the initial phase or epoch is 0, then the motion would begin from the equilibrium position, x is equal to 0, where the displacement is 0. So we will continue from this juncture from our next class. Thank you for paying attention.